Look around you. Notice the space between objects, the gap between your hand and your screen, the emptiness between the stars. We call it empty space. Nothing there. Just a void waiting to be filled. Simple enough, right? But here's the thing. That emptiness you see is not empty at all. It never was. And what fills it might be the strangest discovery in all of physics. I spent decades thinking about this problem. What is nothing made of? It sounds like a philosopher's question, a riddle with no answer. But physics gave us an answer, and that answer changes everything we thought we knew about reality. Let me take you on a journey into the void. Start with something simple. Imagine a perfect box. Remove all the air, remove every atom, remove every particle of light, cool it down to absolute zero. Shield it from every form of radiation. What remains? Your intuition says nothing. Pure emptiness, the absence of everything. Your intuition is wrong. Even in this perfect vacuum, something remains, energy. Not the energy of particles or waves, not heat or light or motion, something more fundamental, energy that belongs to space itself. Think about that for a moment. Space is not a stage where physics happens. Space is an actor in the drama. It has properties, it has energy, it does things. We call this vacuum energy, or zero-point energy. The energy of nothingness. It sounds like a contradiction. How can nothing have something? The answer comes from quantum mechanics, that strange theory that governs the smallest scales of reality, the theory that tells us nature is fundamentally uncertain. Here is what quantum mechanics reveals about empty space. You cannot have perfect stillness, not at the quantum level. The universe forbids it. There is a rule called the Heisenberg uncertainty principle. It says you cannot know both the position and momentum of a particle with perfect precision. But it says something deeper too. You cannot have a field with exactly zero energy. Fields must fluctuate, they must vibrate. Even in their lowest possible state, they retain a tiny amount of energy. These are vacuum fluctuations. The quantum jittering of fields in empty space. Now things get strange. These fluctuations are not nothing, they are something. Particles pop in and out of existence. Pairs of particles appear from nowhere, exist for an instant, then annihilate each other. Matter and antimatter, created and destroyed in the blink of an eye. We call them virtual particles. They are not quite real in the ordinary sense. You cannot catch them or measure them directly, but their effects are real, measurably, undeniably real. In 1948, a Dutch physicist named Casimir predicted something remarkable. Place two metal plates very close together in a vacuum. The quantum fluctuations between the plates are restricted. Fewer wavelengths can fit, but outside the plates, all wavelengths fluctuate freely. This creates an imbalance, a pressure difference. The plates are pushed together by nothing, not by air, not by any force we normally recognize, by the quantum vacuum itself. This is the Casimir effect, and we have measured it. The force is tiny but real. Empty space pushes objects together. Think about what this means. Nothing has power. The void exerts force. Emptiness is not empty. I find this beautiful. The universe refuses to be truly empty. Even when we remove everything, something remains. A fizzing, bubbling sea of quantum possibility. But this raises a question, a troubling question that has haunted physics for decades. If empty space has energy, how much energy does it have? We can calculate it. Quantum mechanics gives us tools to add up all the vacuum fluctuations, all the virtual particles, all the quantum jittering. The answer should tell us the energy density of empty space. And here is where the problem begins. Here is where physics faces one of its greatest embarrassments. When we do the calculation, we get a number, and that number is wrong, not a little wrong, catastrophically wrong. The prediction exceeds what we observe by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This is the worst prediction in the history of science. Something is deeply wrong with our understanding of empty space, and solving this mystery might require rethinking everything. Let me explain why this mismatch matters so much. When physicists calculate the energy of empty space, they use quantum field theory. This is our best description of how particles and forces behave. It has been tested thousands of times. It predicts the behavior of electrons to 12 decimal places. It is one of the most successful theories ever created, so when this theory tells us the energy of the vacuum, we should listen. Here is how the calculation works. Every type of particle has an associated field. Electrons have an electron field. Photons have an electromagnetic field. Quarks have quark fields. These fields exist everywhere in space. They are the fabric of reality. Now each field has a lowest energy state, its ground state. Even in this lowest state, the field is not still. It vibrates. It fluctuates. This is that quantum jittering I mentioned. Each vibration mode contributes a small amount of energy. Add them all up across all possible modes, across all frequencies, across all fields. The sum is enormous. We get an energy density of roughly 10 to the power of 113 joules per cubic meter. That is more energy in a sugar cube of empty space than in all the stars in the observable universe. Think about that for a moment. If this calculation were correct, the universe would behave very differently. This much energy would curve space dramatically. It would rip the cosmos apart. Galaxies could not form. Stars could not burn. We could not exist. But we do exist. The universe is not ripping apart. Something is wrong. Now you might think we simply made a mistake. Perhaps we are adding things up incorrectly. Perhaps there is a cutoff we forgot to include. Physicists have tried every correction they can imagine. Nothing works. The calculation keeps giving absurd answers. Here is the thing that makes this truly strange. We know empty space does have energy. We have measured it, not through the Casimir effect alone, through something far more dramatic. In 1998, astronomers made a shocking discovery. They were measuring distant supernovae. These are exploding stars that serve as cosmic distance markers. By comparing their brightness to their redshift, we can determine how fast the universe is expanding. The expectation was simple. Gravity should slow the expansion down. All the matter in the universe pulling on itself. The expansion should be decelerating. It is not. The expansion is accelerating. The universe is flying apart faster and faster. Something is pushing it outward. Something is overcoming gravity on cosmic scales. We call this dark energy. Dark energy makes up roughly 68% of the total energy in the universe. It is the dominant component of reality, more than matter, more than radiation, more than anything else. And here is the connection. Dark energy behaves exactly like vacuum energy should. It has a constant density throughout space. It does not dilute as the universe expands. It exerts negative pressure. It pushes space apart. The mathematics match perfectly. Dark energy is vacuum energy, the energy of empty space. But the magnitude is wrong. The measured value of dark energy is about 10 to the power of -9 joules per cubic meter. Compare this to the predicted value of 10 to the power of 113. The difference is 10 to the power of 120. 120 orders of magnitude. This is not a small error. This is the most spectacular failure of theoretical prediction in history. We call it the cosmological constant problem. Some call it the worst fine-tuning problem in physics. Here is why it haunts me. Either our understanding of quantum field theory is fundamentally flawed at some deep level, or there is a mechanism we do not understand that cancels almost all the vacuum energy. Almost, but not quite. Think about what that would require. All those contributions from all those fields would need to cancel out with incredible precision. Like adding up trillions of random numbers and getting a result of 1, the cancellation would need to be perfect to 119 decimal places, then fail at the 120th. Why would nature do this? What mechanism could be so precise and yet so imperfect? Some physicists think the answer involves supersymmetry. This is a proposed symmetry between matter and force particles. In a supersymmetric universe, every contribution to vacuum energy would have a partner contribution of opposite sign. They would cancel exactly. But we do not live in a perfectly supersymmetric universe. If supersymmetry exists, it is broken. The cancellation is not perfect. Others think the answer might be even stranger. It might involve multiple universes, different regions of space with different vacuum energies. We exist in this one because this one allows existence. I find this answer unsatisfying, but I cannot rule it out. The vacuum energy problem remains unsolved. It sits at the heart of modern physics like an open wound. Let me take you deeper into this mystery. I want you to understand what vacuum fluctuations really mean, not just as mathematics, but as physical reality. Picture empty space at the smallest scales, not the smooth void you imagine, something far more turbulent. Space itself is foaming, bubbling, churning with activity. At distances smaller than 10 to the minus 35 meters, space becomes unrecognizable. This is the Planck scale. The scale where quantum mechanics and gravity collide, where our current theories break down completely. At this scale, the uncertainty principle does not just affect particles, it affects space itself. Geometry fluctuates, distances become uncertain. The very fabric of reality trembles. We call this quantum foam. Space is not a smooth continuum, it is a seething froth of possibility. Now things get strange. These fluctuations are not just theoretical constructs, they have measurable consequences, real effects that we can observe in laboratories. I mentioned the Casimir effect earlier. Two plates pushed together by nothing, but there are other effects too. Consider the Lamb shift. In the 1940s, Willis Lamb measured the energy levels of hydrogen atoms with extraordinary precision. He found a tiny discrepancy. The energy levels were not quite where standard theory predicted. The explanation: virtual particles from the vacuum interact with the electron. They nudge it slightly. They shift its energy by a tiny amount. This shift has been measured to 11 decimal places. Theory and experiment agree perfectly. The vacuum is real. Its effects are measurable. Here is another example: the anomalous magnetic moment of the electron. Every electron behaves like a tiny magnet. We can calculate its magnetic strength using quantum electrodynamics. But we must include the effects of virtual particles, photons popping in and out of existence, electron-positron pairs flickering briefly. When we include all these contributions, we get a prediction. This prediction matches measurements to better than 1 part in a trillion. The most precise agreement between theory and experiment in all of science. Think about that for a moment. Virtual particles that we cannot see directly, fluctuations we cannot observe in isolation. Yet they contribute to measurable quantities with extraordinary precision. The vacuum is not nothing. It is everything in potential. Here is the beautiful part: these vacuum fluctuations might be responsible for everything that exists. Let me explain. In the very early universe, moments after the Big Bang, the cosmos was unimaginably small. Quantum fluctuations that are normally invisible were stretched to cosmic scales. These tiny ripples in the vacuum became the seeds of all structure. Regions of slightly higher density attracted more matter. They grew into galaxies. Regions of slightly lower density became the voids between galaxies. Look at the night sky. Every galaxy you see, every cluster of stars, every cosmic web of matter stretching across billions of light years, all of it came from quantum vacuum fluctuations. Stop and think about what this means. The randomness of the quantum vacuum determined where galaxies would form. The uncertainty principle shaped the large-scale structure of the universe. Nothing created everything. I find this profound. The same vacuum energy that puzzles us with its magnitude also explains our existence. Without vacuum fluctuations, there would be no structure, no stars, no planets, no life. The void is our mother, but here is what troubles me. If vacuum energy is real, if it has measurable effects, why is its gravitational effect so small? Why does it not curve space dramatically? Why is the cosmological constant so tiny compared to our predictions? Some physicists have proposed a radical answer. Perhaps the vacuum energy does curve space, just not in the way we expect. Perhaps it curves extra dimensions, dimensions we cannot see, dimensions that are curled up so small that their effects are hidden from us. This is the idea behind string theory, a framework where space has not 3 dimensions but 10 or 11. The extra dimensions are compactified, rolled up at the Planck scale. In string theory, vacuum energy might flow into these hidden dimensions. It might curve them instead of curving our visible space. This could explain why the cosmological constant appears so small. But we have no evidence for extra dimensions. Not yet. The idea remains speculation. Other physicists suggest something even more radical. Perhaps vacuum energy gravitates differently than other forms of energy. Perhaps gravity itself behaves unexpectedly at quantum scales. This would require modifying Einstein's general relativity, the theory that has passed every test for over a century. That is a drastic step, yet we might have no choice. The vacuum energy problem sits at the intersection of quantum mechanics and gravity. Solving it might require unifying these two theories, a quantum theory of gravity, the holy grail of physics. I spent much of my career searching for this unification. I made some progress, but the full answer eluded me. It still eludes us all. Let me bring this journey to a close. We began with a simple question. Why does empty space have energy? Now you see that this question leads to the deepest mysteries in physics. The vacuum is not empty. It seethes with quantum fluctuations. Virtual particles dance in and out of existence. Fields vibrate even in their lowest states. This is the nature of nothing. We have measured these effects. The Casimir force, the Lamb shift, the electron's magnetic moment. The vacuum is real. Its energy is real. And yet we cannot explain its magnitude. Our best theories predict a vacuum energy that would tear the universe apart. Instead, we measure a value 120 orders of magnitude smaller. This discrepancy is the cosmological constant problem, the worst prediction in the history of science. Here is the thing that keeps me wondering. This tiny vacuum energy, this dark energy, is exactly large enough to matter. It dominates the universe today. It drives cosmic acceleration. It determines the ultimate fate of everything. A little larger and galaxies could never form. A little smaller and the acceleration would be undetectable. We exist in a universe with a vacuum energy that is just right for us to exist and observe it. Coincidence? Fine-tuning? Or something deeper? Some physicists invoke the anthropic principle. Perhaps many universes exist with different vacuum energies. We find ourselves in this one because only this one permits observers. This is not an explanation. It is a selection effect. I find this unsatisfying. It feels like giving up, like admitting we cannot understand why the vacuum energy has its particular value. But perhaps that dissatisfaction is misplaced. Perhaps the universe owes us no explanations. Perhaps reality simply is what it is. Perhaps asking why is the wrong question. I do not believe that. I believe nature is comprehensible. I believe the vacuum energy problem has a solution, a real solution that we have not yet discovered. Think about where physics stood a century ago. We did not know atoms had structure. We did not know about quantum mechanics. We did not know about the expanding universe, the Big Bang, black holes, neutron stars, dark matter. All of this was discovered in one human lifetime. The next century might bring equal revelations. A quantum theory of gravity, an explanation for dark energy, a resolution to the vacuum energy puzzle. I will not live to see it, but you might. Here is what I want you to understand. Empty space is the foundation of reality, not matter, not energy in its familiar forms, the vacuum itself, the seething quantum foam from which everything emerges. The particles that make up your body are excitations of quantum fields, ripples in the vacuum. You are a pattern of disturbances in nothing. Stop and think about what this means. The boundary between something and nothing is not sharp. It is blurred by quantum mechanics. The vacuum constantly creates and destroys particles. Matter is borrowed energy from the void. You exist because the vacuum fluctuates. The stars exist because the vacuum fluctuates. The entire visible universe exists because the vacuum fluctuates. Nothing is the mother of everything. I find this beautiful beyond words. The universe could have been simple. Empty space could have been truly empty. A dead void with no energy, no fluctuations, no potential. Instead, nature chose complexity. The vacuum teems with activity. It has energy. It has structure. It has the capacity to generate everything we see. Why? We do not know. How? We are still learning. But that we exist at all, that anything exists at all, might be the greatest mystery of all. The vacuum energy problem is not just a technical puzzle. It is a question about existence itself. Why is there something rather than nothing? And why does nothing have so much something in it? I spent my life studying black holes and the origin of the universe, but I always return to this question. What is empty space made of? What is nothing? The answer is not nothing. The answer is everything in potential, a sea of possibility, a quantum foam of creation and annihilation. We are creatures of the void, born from fluctuations in nothing, sustained by the energy of emptiness, destined to return to the vacuum from which we came. That is not a sad thought. That is a profound one. We are how the universe knows itself, how empty space wonders at its own nature, how nothing contemplates something, and that is the beautiful part. The vacuum has energy. That energy created everything, and everything includes you, asking why the vacuum has energy at all. The question contains its own answer. You are the vacuum, awakened.